Jai Hind and good morning. I am Professor Devendra Singh. In this lecture, we will try to solve two more problems on elastic constants. During the last three lectures, we have discussed about the elastic constants, Hooke's law, and the relationship between various elastic constants like modulus of elasticity, modulus of rigidity, uh, bulk modulus, and Poisson ratio. We have discussed in the last three lectures. Two problems we have attended in the last lecture to determine the elastic constants. Like in first problem, we have determined the Poisson ratio based on the values of modulus of elasticity and modulus of rigidity was given, and it was a direct problem. To determine the new, we must recall our relationship between modulus of elasticity and modulus of rigidity, that is E is equals to 2g 1 plus nu. That relation we have applied in that very first problem, where E and G were known and nu was determined in that problem. In second problem, we have been given a data from the test performed on universal testing machine, and we asked to find out the values for modulus of elasticity. Then we asked to find out the value of percentage of elongation, percentage of decrement in the area. So from that, we have used our Hooke's law, and Hooke's law is valid up to the elastic point or elastic limit of the material, and Hooke's law states that sigma is directly proportional to epsilon, that is stress is directly proportional to strain. So we use this relation that implies that there is a linear relationship, and corresponding to this relation, we determine the deflection at the elastic point, because the deflection at the elastic point was not given in that problem. Only the deflection corresponding to a particular load, that was 160 kilonewton, I think, and it was known what was the deflection corresponding to this load, but at the elastic point, what's it by the deflection, it was not given. So we have a relation P P upon A is equals to E delta upon L. That is nothing but it is the modification of sigma is equals to E epsilon. Epsilon is deflection upon the length, original length, and sigma is equals to force upon area. So we have determined P upon PE upon P is equals to delta E upon delta. So we can find out from this relation what is the deflection at delta E at the elastic point corresponding to PEP was given the reading obtained from the test, and then we determine the stress at the elastic point, and final measurements of the lengths and the diameters were given. So percentage of elongation and percentage of decrement in the area was quite simple, but it was the application of the Hooke's law. Again, we will try two more problems on the same topic. This is the first problem. There is a bar of 25 millimeter diameter is given, 25 millimeter. It is given, and it is subjected to a pull force of 40 kilonewton. 40 kilonewton is a load, and it is written here 40,000 Newton. Again, I emphasize because I use the units as Newton per mm square. So kilonewton, I convert it into Newton, although there is no problem if you are using this unit in kilonewton, no problem. Gauge length is given 200 millimeter for this bar, and the elongation in this bar is 0.085 mm corresponding to this load, and the change in diameter is 0.003 3, because whenever you increase something, then the volume of the material will remain same. So if you increase, the length increases, then the diameter or the lateral dimension will decrease, the area will decrease. So here is a decrement in the diameter, that is 0.03 mm. Now we need to determine what. First is what is the Poisson ratio for this material, that is the first part. Then what should be the modulus of elasticity, that is second part. Modulus of rigidity, that is third part. And bulk modulus of this material, that is fourth part. So these four elastic constants we need to find out for this bar material. So we start this solution. First is the Poisson ratio. So by definition, what is the Poisson ratio? Poisson ratio is the lateral strain upon longitudinal strain. From the data, we need to find out what is longitudinal strain, what is lateral strain. The elongation is given, the change in the diameter is also given. So we can easily find out what is the longitudinal strain, what is lateral strain. So first we write what is the Poisson ratio. Epsilon T is the transverse or lateral strain upon epsilon L, that is longitudinal strain. So what is epsilon L? That is longitudinal deflection upon the gauge length. Delta L is given in this problem, that is equal to 0.085 mm in the length of 200 mm. So epsilon L will come out 0.000425. That is epsilon L. Strain is non-dimensional quantity, millimeter upon millimeter. So unit is, this is not having any unit. Right. Now find out what is epsilon T. So in epsilon T, because this is the change in the diameter. So change in the diameter upon original diameter is lateral or transverse strain. So if I put the value of delta T, it is given in the problem, that is 0.003 upon 25. So it is 0.00012. Again, this is dimensionless as it is a strain. Now, if I put the value epsilon T upon epsilon L, we will directly get the value of Poisson ratio. So this is 0.00012 upon 0.000425. So Poisson ratio for the material of the bar is 0.28. We have determined. Now the modulus of elasticity. And in the last lecture, we have also determined the modulus of elasticity. So up to the elastic limit, stress is directly proportional to strain, or stress is equal to E into epsilon. That is the basic thing. So within the elastic limit, E is equal to sigma upon epsilon. Epsilon L, we just have determined the last step. So sigma, we need to calculate here. So E is equal to sigma upon epsilon L. This is the expression of the Hooke's law within the elastic limit. Epsilon L we have already determined 0.0000425, the last step. So sigma is equal to P upon A. P is given, how much load is applied, the diameter is given, so area can be easily calculate. So we will put the value sigma is equal to P upon A, that is equal to 4 into P upon pi into D square. Just put the values. The load is given 40 kilonewton, that is 40,000 Newton divided by pi into 25 square. So sigma is equal to 81.49 megapascal, or in Newton per mm square. Sigma is known, epsilon L is known. So the ratio of sigma upon epsilon L is modulus of elasticity for this material. We just put this value in this expression and we can get the modulus of elasticity. So E is equal to sigma upon epsilon L. Putting the values, it is 1,91,741.18 megapascal. This is megapascal. The modulus of elasticity, modulus of rigidity, and modular bulk modulus, these are normally we get in gigapascal. So we can easily convert it it will be 191.741 gigapascal, or up to the second place of the decimal, it is now 191.74 gigapascal modulus of elasticity. So we have determined the second elastic constant, modulus of elasticity. Now we move to the third one, that is determination of modulus of rigidity. Now we have determined the modulus of elasticity and Poisson ratio, and we have to determine or decide the modulus of rigidity. Very simple. We just use the relation we have already established between modulus of elasticity and modulus of rigidity. So the relation is E is equals to 2G1 plus nu. In this relation, E is known, that is modulus of elasticity we have just established. Nu we have determined very first step, so G can be easily find out. So how will you find G? This is G is equals to E upon 2, 1 plus nu. Just put the value of E and nu, we will get what is G. You will just put 191.74 gigapascal, 2 times 1 plus 0.28, that is nu, and answer comes out 74.90 gigapascal for this material. Third, elastic constant we have determined. Now the last is the determination of bulk modulus. Again, modulus of elasticity, Poisson ratio, and modulus of rigidity are known. We have determined. Now the problem is to find out the bulk modulus. So we will again use the simple relationship between modulus of elasticity and bulk modulus. We can use the relationship between EGK also. So in my opinion, because we are known this modulus of elasticity E and nu, so that relationship is better to use here. So we use this. E is equals to 3K1 minus 2 nu. From here, K is equals to E upon 3 times 1 minus 2 nu. K is the bulk modulus. We just put the value of modulus of elasticity and the nu in this expression. We will get this 145.26 gigapascal. This is gigapascal because this value I put here in gigapascal. Nu we have determined in the first step. So this is the answer for the bulk modulus. So in this way we have determined all the 4 elastic constants from the given data. Now one more problem we will try. Here the answers are shown. Poisson ratio we have determined 0.28. Modulus of elasticity of the material bar is 191.74 gigapascal. Modulus of rigidity is 74.90 gigapascal. Bulk modulus is 145.26 gigapascal. Now this problem is having 2 materials. One is steel, other one is brass. So here we have a steel wire which is 2 meter long and 3 millimeter in diameter, is extended by 0.75 mm by a weight W. This magnitude is not known to us. Is suspended from the wire. If the same weight is suspended from the brass wire, this is second material is brass, and it is 2.5 meter long, and the diameter is 2 millimeter, and it is elongated by 4.64 millimeter if we are applying the same pulling force on the brass. Now we need to find out the modulus of elasticity of brass. Modulus of elasticity of brass, if the modulus of elasticity of the steel is given 2 into 10 to power 5 Newton per mm square. This is a problem. So in the very first step, we will try to find out what is the load W. Once load is known, then the length is known of this brass material or brass wire, diameter is known and elongation is known. So we can calculate what is sigma, what is epsilon, and within the elastic limit, we can use the Hooke's law to determine the modulus of elasticity. So we will try to attempt this problem. First, what is given for steel wire? Length of steel wire is 2 meter, that is 2000 millimeter, diameter is 3 millimeter, and the elongation is 0.75 millimeter, and modulus of elasticity 2 into 10 to the power 5 Newton per mm square. For brass wire, length is given 2.5 meter, that is 2500 mm. Diameter of the brass wire is 2 millimeter. Diameter of the brass change elongation delta B is 4.64 millimeter. The deformation are under the effect of the same load W. So first step, we should find out what is W to determine the modulus of elasticity. We need to determine EB. EB is the modulus of elasticity for brass material. So stress induced in the steel wire, that is our objective. For that, we need to find out this load W. So according to Hooke's law, sigma is equals to E into epsilon, and sigma is equals to ES into delta S upon A Ls. If we further put the values 2 into 10 to the power 5 into 0.75 upon 2000 equals 75 Newton per mm square. These are the known values. So stress for steel wire we have determined from the available data, that is 75 Newton per mm square, and this sigma is load upon area. So the diameter of the steel wire is given, sigma we have determined. So we can determine sigma is equals to W upon A. So W can be determined. That W we will apply on the brass wire, and for the brass wire we will analyze and we will determine the modulus elasticity of the brass. Right. So determination of W stress is equals to W upon A. Here sigma is equals to 4 times W upon pi into D square. So 75 Newton per mm square, 4 times W divided by pi into 3 square. The diameter of this steel wire is 3 millimeter. So we have put all the values. W is unknown. So we can find out what is W. W is 530.143 Newton. That is W. Load is known. If load is known, this load we apply on the brass wire. So stress can be easily find out how much stress will be induced in the brass wire of 2.5 mm diameter. So stress induced in the brass wire due to this load W, sigma B is equals to W upon A, and this W upon A is pi by 4 into D square. We have already used here. This is the same. So 4 times 530.143 divided by pi into 2 square. This 2 millimeter is the diameter of the brass wire. So stress induced in the brass wire is 168.75 Newton per mm square. Now we need to determine the strain in the brass wire. If it is known, then sigma is equals to E epsilon. So E can be easily find out sigma upon epsilon. So next we will determine the longitudinal strain. Epsilon B is equals to delta B upon LB. Delta B is given, that is 4.64, whereas the length of the brass wire is given 2.5 meter, that is 2500 or 2500 millimeter. So epsilon B is equals to 0.001856. So now we have a stress, we have a strain. Apply simple the Hooke's law and determine the modulus of elasticity of the brass wire. So determination of modulus of elasticity of brass wire. Sigma is equals to epsilon B into EB. So EB is equals to sigma B upon epsilon B. Sigma b is known, epsilon b is known. Just put the values of sigma b and epsilon b in this expression. We will get 168.75 divided by 0.001856, and it will come out 90,921.336 Newton per mm square. It is dimensionless. It is dimensionless, and it was in Newton per mm square. That's why this is in Newton per mm square. Now write it in megapascal or gigapascal. So Newton per mm square is equals to megapascal. If we want to convert it in gigapascal, we have to further divide it by 10 to power 3. So it will become out 90.921 gigapascal or 90.92 gigapascal for the second place of the decimal accuracy. With this, the elastic constants are over. In the next lecture, we will try to learn about the deformation of various bars subjected to axial loads. Due to their self weight, also we will include later to determine the deformation. So we will meet again in the next lecture with the deformation in bars under axial load as well as due to self weight. Thank you. Thank you very much.